Right, guys, welcome back to the second chapter of the Smol training playbook. And you can see my screen now, right? And it shows the slides and everything.
Yeah.
Cool, cool, cool. Just would be like pretty terrible if it didn't. But all right, cool. You have the slides. All right. So today we're going to talk about the second chapter about ablations. And as I said in the opening conversation prior to the recording, I don't have like a ton of experience with ablations. I mean, like probably like most of us, I did some ablations, but I wouldn't consider myself an expert. So if you have anything to add at any time, feel free to stop me and contribute to the conversation. And once again, please sign up to present new chapters. So without any further ado, let's begin. So every model starts with a small ablation. Basically, what they're trying to tell us is that we should roughly follow this blueprint: experiment, fail, and learn, instead of trying to to theorize. Well, basically, just try to play everything, try to come up with a perfect solution in our heads. Um, because it's kind of well, ML, machine learning is, I'd say, vastly empirical science. So without running experiments, you can try to come up with perfect architecture in your head, but it's not worth much unless you try to actually apply it somewhere. So they recommend to do ton and ton of experiments, fail fast, learn on them, and iterate. Well, makes sense. Move fast and break things, right? So I heard this motto somewhere. And one of the first things, as an example that they present, is that, for instance, when you're training a mathematical reasoning model, probably you would assume that training on high quality archive, whatever, the main storage for um, machine learning research thing, archive, papers would be the best approach. However, for small models, and I'd like to highlight that for small models, exactly, it doesn't reflect real life. If we take a look at this, at the results on training two small models, 1.3b and 7b, with no math training. I mean, like no dedicated math training, and I don't remember which data mix they have by no math training, but probably well, something like generalist-ish math pile, and archive red pajama, which I believe is a um, deviation from math pile, but it's based on math pile. We can see that on some on some benchmarks, we see that this archive training produces superior results, but overall, no math training produces better results on quite a few other benchmarks. And I mean, it kind of makes sense to um, have better results for MMLU, because MMLU, if you don't know what it is, it's a huge eval data set, 12K rows, and it spans across, I think, 12 different domains. So it kind of makes sense that the model that was trained on like a very diverse data set performs better than the model that was trained on the fairly narrow data set. But we can see that even CMath and other mathematical benchmarks also also perform better with no math training compared to training only on the archive data, which tells us something about the quality, well, not quality, about the importance of the diversity of the data set. However, um, the authors in the book omit one crucial thing, in my view. I mean, they say that it's specifically for small models, but I'd like to highlight that it's very important that this finding is true only for small models. They didn't evaluate it for large models. And I think that for large models, it can be, the picture could be different. The reason for that is that, well, kind of in my current research, we tried to um, find a subset of the data that contributes the most to the outcome of the training. And we saw that if we train on the easiest data, we used entropy, but that's beyond the point. So like if you split your data set in some reasonable manner, starting from easy and ending with hard. So if you train on easy data, model gets dumber. But if you train on the very hard data, the data that the model can't absorb right now, model also gets dumber. It's like you see an initial rise and then a hard cliff. So I'd say that, well, not say, but claim, or at least question, if if we train a fairly large model on the archive data, would it be the same? Would it produce the same results? That's a question still standing, in my view. But nevertheless, going further, baselines. So, tadam, tadam, they say that, hey, most of the well-known open source models, they used all the versions of these models as baselines, all the versions of like solid, robust, well-proven open source models. And here are the rules of choosing these baselines. Basically, matching your constraints. So I guess by matching your constraints, it doesn't make sense with certain caveats, but overall, it doesn't make sense to compare your open source model that can be deployed everywhere to closed source model that like lives somewhere in the other cloud. I mean, like you can, but your better baseline would be another open weight model that can be deployed somewhere else. But I'd say that probably what they even mean that, say, if you want to deploy on some custom hardware, for instance, if we're developing a machine learning model for a smartwatch, then it doesn't make sense to compare our model with a model that can run in the cloud utilizing hundreds of GPUs. Be proven at scale. I guess what they really mean here is not that the model should be proven at all scales. The model should be proven to work. About like the baseline should be proven to work at our scale. So if we're training like a 1D model, we should know that the current, like the architecture that we saw previously in the baseline works for that size. And it goes both ways, right? So it doesn't make too much sense. Like it doesn't make a very strong baseline if you saw an architecture that works in small models and then you try to apply it to big models. It doesn't qualify as proved. But same applies in the reverse direction, and I think that's often frequently overlooked. If there is an architecture that works on big model, it's not going to work necessarily on small models. Well documented, known hyperparameters, and etc. etc. Well, because we want to not only take the open weight model trained somewhere, probably we want to alter it in some way, right? We want to train the same architecture, or maybe do continuous pre-training, maybe do fine-tuning, but well, keep training, but probably better train from scratch. Um, with some tweaks, right? So maybe we want not just to take pure Llama 2. We want to take pure Llama 2 and maybe add, I don't know, new attention style there or something like that. At least that's my understanding. And have good framework support, meaning that it's a baseline. It's not our core model. So it doesn't make too much sense to create custom infra for training baselines. All right. Solid standard baseline is much, much better than flaky, artisan, cool, bleeding edge rocket chip. And what they mean by that is that they introduce this concept of de-risking. which means that if we want to tweak our baseline, for instance, add I don't know, add a new positional embeddings or anything else, we need to have a good intuition about how this change could positively, potentially positively affect the performance in some measurable, meaningful way. And I repeat, measurable. Um, and also, it should perform consistently. So it's across maybe multiple runs or across one long run. We shouldn't see like spikes of the metric that we're trying to optimize for. So it shouldn't look like we randomly guessed and because of some stochastic something we got better result. It should be we should have a very, very good um ties between what we changed and the results that we got predicted before we actually made the experiment, right? Well, they also talk about strategic experimentation. Um, Basically that knowing how to run experiments, it's not enough. Uh, we need to know which experiments are worth running, and I guess we already covered that, right? So we have limited resources, and we can't just usually, especially like if we experiment at a fairly large scale, we can't just start a hyper like grid search across all of the hyperparameters. However, I mean, like if you have the resources, personally, I don't see an issue with that. But let me know if you have any other um, approach here. All right, then they talk about frameworks. And they present us with four, I guess, most popular and most established frameworks: Megatron LM, DeepSeek, Torch Titan, and Nanotron. And I guess Nanotron, it's kind of, well, it's Hugging Face baby, and they include the Hugging Face baby in their comparison table. I'm not sure how many people really use Nanotron these days, but well, it's there. But from what I heard and based on the technical reports that I saw, it's usually Megatron or DeepSeek. And sometimes I saw Torch Titan on Twitter and on Reddit. Um, and in terms of battle testing, we know that Megatron powers Kimi K2, and DeepSeek powers Bloom and JLM. And I don't think I saw Bloom in any recent comparisons, but GLM I did, so good stuff. But let's go a little beyond the book. I'd say there are few notable mentions. LLM Foundry from Databricks. Um, I know that one of the Russian labs uses a fork of that. And well, Databricks use it, and Databricks is huge. Levanter, it's made for JAX and TPUs. So if you want to kind of squeeze every last bit of your performance and want to play with Google hardware, by all means, go there. Facebook Research produced Lingua, and we have a fantastic code base. Uh, Completely open source for Alma models by AI2 Lab. And I'd like to highlight one thing from the book that ultimately our choice will depend on the team's expertise. And in my engineering experience, if you start a new project, don't really try to find the perfect framework. Um, I mean, try to find something that works that fits the best to your requirements. But if your team already knows something, probably velocity at which they can operate and start experimenting means much, much more. In my personal experience, many, many times I went not with the ideal technology, but with the technology the team already understands and knows. But once again, if you have different opinions here, by all means, feel free to contribute. Do we have any different stories? All right, then probably later.
Yeah, I unmuted, but yeah, so regarding the team's experience, sometimes it's like, yeah, this point is totally valid. Sometimes it's also restrictions by the like company rules or something. So customers not allowing something and some legacy code, some integrations. So not it's always a negotiation between what makes sense to start fast, what makes sense to like how we foresee it on long perspective, on short horizon. But yeah, I support the idea to start at least with something instead of my common mistake is choice paralysis. So I observed that it's much easier with job. So yeah.
Sure, sure. And I guess maybe I was just personally hurt in the past, but I'm coming from web, and at some point in time, back in time, I was working a lot on the front end part of the web, and that's like there is such a huge obsession over new frameworks and libraries, and sometimes I saw one of the teams trying to actually rewrite an already functional app into a new framework without any good reason to do so because it already worked fine. They just like, hey, this is new shiny thing, everybody uses it now. Like, what? I don't know. I was crying out loud.
Yeah,
Well,
there was only one interview in my life, like for the customer, when I wasn't accepted for the project, when they were looking for somebody working with React. And I worked with Angular before, but like I worked with Angular just like I never knew Angular before I started working with it being on a project. So it was kind of hilarious to me. So I didn't like the project anyway, so it was a perfect excuse for me also not to come there. But and I actually grateful to that interviewer from the customer side who decided like no, we just no need person who knows this framework but not the others.
Sure, happens all the time.
oh yeah, on that I could agree with both my hands. So I've seen this situation many times when the research team decided that all the existing frameworks are not good enough, like they are not tailored to their needs and so on and so far, and they come up with a beautiful idea on how it should be structured and rewritten or implemented from scratch. 6 months later, they end up with the same gigantic framework. Again, no one understands how it works, how to debug it, and so on and so forth, but they are happy. Common story.
Well, at least the team was happy. I mean, as long as
Yeah,
they're
sure.
happy, over the years, I kind of came down to one conclusion that I'd say that the psychological health of the team and keeping the team motivated is, well, if not the most important thing in the long run, it's like it's very high on the list of priorities for me. So I'd say if the team is happy, it's good result, really.
Yeah, with that can agree as well. The sole limitation here is the burn rate. So if you are off the schedule with your product, well, it's not a good time to implement a new framework. If you have lots of time for research and you have money for that, surely it makes sense to invest in the tooling.
Sure. Well, we just need to make sure that no one of the like C-level guys, no one of the executives hears this talk, so they don't like ever question when we tell them that we need to write everything from scratch. All right. So, goal of ablations is to run experiments at small scale and get results that we can confidently extrapolate to our final production run. And in my view, it goes beyond that. The goal of ablations, in my view, is also to run experiments, well, at small scale to kind of to use less resources to get potentially like extrapolatable results, but also to experiment in isolation to kind of figure out um, which part of the pipeline that we tweaked produces the most results, and how do they kind of contribute, like what percentage of the final result they contribute to the overall achievement, overall increment, overall gain. Um, so what the authors propose is to train fewer tokens, so train a smaller proxy, and they reasonably mention that when we train a smaller proxy, it's kind of questionable like how the scaling laws are going to work. Is it going to be transferable? And the like rule of thumb here is that, well, let me do the highlights. If something hurts performance at small scale, it's definitely going to hurt performance on the large scale. But if something works at small scale, it's um, it's not going to necessarily work at large scale, and we need to make sure that we train on reasonable number of tokens. That number of tokens scales reasonably well from small model to large. And I mean, like, uh, say we if we don't if we forget to adjust the number of tokens that we train when we go from large model to small, it means that we kind of feed more information into the small model in relation to how many parameters it has. So it's not a fair comparison to the large model performance, right? Um, and also, I think once again, it goes both ways. If something works at large scale, it doesn't really, it's not really going to, it doesn't have to work at small scale. And I'd say that probably we'll never ever run ablations at large scale to prove that something works at small scale. But if we're borrowing ideas from papers that I don't know, hey, something worked for this DeepSeek R1 with what 600 billion parameters, it might be not the best idea to apply it straight. Well, it might be a good idea, but it's not guaranteed to work for your 1B model. Well, obvious stuff, but still worth saying that modify one thing at a time. So change only one variable per ablation. Blah 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 blah. Thanks. But no, I mean like really thanks, but kind of obvious. Hopefully, never forget that. Warning. Some architectural changes can significantly alter the parameter count. Adjust hyperparameters accordingly. I'm wondering if well, they had an example in the book. I don't think it was like very relevant. Just like always keep in mind that whenever we change the model size, we also need to adjust the amount of data that we train on and adjust other hyperparameters accordingly. And they produce this with a wonderful visual tool that's available on the book's website. But don't think it's worth commenting here. It's just like it's there. Play with it if you need to. Um, and last thing, evals provide much better information than your loss curve, and they have a correlation, but lower loss not always means better evals. And they give us a few kind of criteria on how to choose evals. They have to be, and I don't agree with all of the criteria to be honest, but that's later. Uh, Monotonicity. So yeah, like your benchmark scores should consistently improve. So the kind of eval loss should consistently go down as model trained longer. Low noise. Um, Meaning that if we do multiple runs of training, that benchmark scores shouldn't vary wildly, which makes sense unless uh we are trying to maybe maybe not unless. I think this is true at all times. I was going to say that maybe if we're playing with different initialization strategies, but different initialization in my mouth and tongue are not working today. But different initial you got it. Different strategies to initialize. They don't really assume different random seeds, they assume different distributions. And so it's not about random seeds. About random performance. Um, this stuff is where I disagree, kind of. So, but like, who am I to disagree? But still, uh, they say that some capabilities only emerge late in training, so it makes sense to pick tasks that kind of demonstrate consistent performance across the entire training run, kind of monotonicity, and it goes hand in hand with ranking consistency, meaning that if one approach outperforms another at early stages, this ordering should remain stable as training continues. And to be honest, I have a couple of comments here. It's like, well, what about if we want to test emergent abilities? Like, what if we want to see, like, I think there was a huge obsession about emergent abilities in LLMs um, several years ago when we saw that, hey, if we go large, so like LLMs can magically start generalizing things. So it's like, how do we pick an eval that ranks consistently if we trying to peek into the emergent abilities, and like, why does it even matter that much? Like, say, I mean, I get that without ranking consistency we can claim that it might be random, but if we do multiple training runs with different random seeds, why is it not okay for us? And across different training seeds, we see the same ranking consistency shift. So maybe like after 10 epochs of training, we see that the model, uh, like training approach B, starts outperforming approach A consistently. So we see this rank shift. Why is it not acceptable? This is unclear for me. Um, and it goes hand in hand with above random performance, at least in the way that they presented here. Uh, I mean, like, if some evals start producing results only later in time and they produce like fairly random results uh, in the early stages, could we kind of dynamically change our evals as we train? Or maybe even actually run the evals at all times? Because if we have an eval benchmark that um, performs well at early stages, could it be the case that it works well at early stages, but it's not as meaningful at late stages? For instance, we train, like, our eval is something fairly simple, and the model can work with this eval and can improve on this eval at early stages, but then the model gets, like, both of the approaches get fairly advanced in that domain of the eval, and they saturate the benchmark. They saturate the eval. So I have a couple of questions here. Um, do we have any comments on this slide? Because like, I made a lot of assumptions. Curious to see if you guys agree or disagree. All right, three, two, one. I'll take silence as complete and unchallenged agreement with all that I have said. Well, at last, maybe not at last, we'll see. But at last-ish, they tell us about different styles of benchmarks. So, styles of evals, multiple choice format, close formulation. I'm wondering why it's with Z, not S, but close formulation. That's how it was in the book. And free form generation. MCF, it's like, well, you ask model something and it picks an answer from a predefined list of options. Close formulation is, well, you kind of assess the result against the, um, like how close it is to the ground truth, I guess, in a sense. And freeform generation, well, I guess you just ask the model to produce some like arbitrary output, for instance, maybe like generate me I don't know, some fiction book, right? And you somehow try to assess the quality of the structure of the text and the quality of the uh, imagination of the model in various ways. Probably model is judge, but anyhow. Um, and they kind of tie this different versions of the benchmarks of the evals back to what they said before about the criteria that research also shown that small models, I guess small models specifically, struggle with MCF early in training, making CF better for early signal. And that's how they justify using CF for small ablations and integrate MCF in the main run when they train a larger model. Um, and we can't do the ablations not only on the architecture, but also on data. And in that regard, we take the opposite approach. We fix the architecture and we try to play with different data mixtures and different data subsets. Um, and at last, yes, this time is really at last. At last, it's also worth keeping track of how much resources you spend on different stages. Well, to first be very open with the community, but also to probably have a good idea for the future trainings about how much time it's going to take to run ablations and how much time it's going to take to debug. And here we can see that the main training run, it's roughly about half, well, a bit more than half, but roughly like 60%-ish of the final GPU hours. And the rest is ablations and training reset debugging. And when I see these numbers, in my personal experience, probably the engineering team there is just like superstars. Because in my personal experience, when I develop something sophisticated, and I'd say that training large language models at scale qualifies for sophisticated, I'd expect to spend on debugging at least half and maybe the same amount of time as I spent on the main thing. So, like, they did a fantastic job there to debug everything and to do train resets. Or maybe they debug everything at ablations. I'm not sure, but anyhow, I would expect an even larger number for debugging. Maybe I'm just dumb, who knows? And also ablations. So we can see that ablations only took them, well, what? Roughly a third of their main training run. Um, and well, probably it's because like it's open source, so fairly limited cache, I'd expect, and maybe like the final main training run is not that large. To be honest, I'd expect uh a company to be spending more on ablations if they want to train a very, very, very large model. I think we saw this in the past. When the company first runs very small ablations, they produce some intermediate model of like, well, fairly large, but not the largest one. And this intermediate model, we take it as a final product. But in my mind, and based on what I see on Twitter, Reddit, and everywhere else, this kind of model that they produced, this is another ablation actually. So when they produce, I don't know, a 70B model that might be a result of an ablation and it might be a result of preparation and developing a baseline for their 1 trillion model. At least that's how I think about it. All right, conclusion. So, ta-da! Validate your evaluation suite. Blah. Sorry for my language today. So before training any models, do manual intervention and see what the actual data is, especially if you have suspiciously good results or suspiciously bad results. But anyhow, manual intervention inspection is mandatory to evaluate that the model produces something reasonable and not complete garbage, and that comes from my personal pain as well. Test every change, no matter how small. Well, kind of obvious, hopefully. Change one thing at a time. Well, once again, we count that, so to be able to differentiate between different changes in the architectural dataset, we need to change only one thing at a time. And train on enough tokens and use sufficient evaluations. Well, for training on enough tokens, I think we have good research there, the like good empirical data to get a sense of what is enough. Um, but like using sufficient evaluations, I think this is like a bit of thank you, authors, really. The book is great, but it's like a bit of wishful thinking in my view. Like, what is sufficient? How do we know that we don't know something? Like, how do we reduce this epistemic uncertainty? But anyhow, like, try to do your best, I guess. So this is it from me for today. Do we have any comments or questions? And three,
Thank you.
2, 1. Thank you for coming today and see you next week for, well, I guess we'll start playing with architecture and we'll take it bit by bit. I guess we'll start with attention, but we'll see. I'll post it in the group. So, yeah, I guess see you around, guys. And I'm stopping the recording.